Welcome to part 5 of Not the Ideal Medium for Teaching Physics. In the last section, we were talking about how waves were overlapping when they go through a single slit. It's called single slit diffraction. You can think of each light wave as spreading out kind of like a wave in water. There are 4 quanta of lights, each spreading out like a wave in water. Where they hit, they form constructive interference. Where they go straight out, they all travel the same path length, so they arrive in phase. This gives our central maxima. We can say that the waves head straight forward and interfere with each other to produce constructively. I think that's how you spell that word. Now we are going to talk about this third diagram. When we have light beams that are not going through the center, we get a different result. Let's say that each light wave has a friend that's a distance of half the slit away. If the slit has a length a, then each wave's friend is a distance of a over 2 away. So the distance between 1 and 2 would be a over 2. Let's erase 3 and 4 for clarity. Now we have rays 1 and 2. Rays 1 and 2 travel different path lengths, just as we saw in the chapter, just as we saw on the pages before. If we set them so that they're both traveling the same path length, then we end up with the difference of them. So from here out and here out, R1 equals R2. We've cut off this little extra bit on the side. This triangle here can be redrawn like this. And we can also get an angle of theta. This angle here is actually equal to that angle there. From this theta value, we can determine the angle to each maxima. We can use the same principles to find minima. So minima occur where this offset is equal to lambda over 2, so half a wavelength. We can find the positions, so we can draw out this triangle like this here. From this, we can get that delta R is equal to A over 2 sine theta. Finding the minima, we set delta R to lambda over 2, and we get lambda over 2 equals A over 2 sine theta. We can rearrange this for a general condition for complete destructive interference. I'm going to change that to a hard arrow. Our general condition is A sine theta. This one is a subscript of P. Sine theta P equals P lambda. A is the slit width, theta is the angle, P is the number of minima, so P is like M, but for minima. And lambda is the wavelength. So theta p is the angle to a dark fringe. From the small angle approximation, we know that if theta is much, much less than 1 radian, sine of theta is approximately theta, giving us theta is equal to P times lambda over A. I wrote that wrong in my initial notes. So that would say that theta is equal to P times lambda over A. It's important to note that these angles are in radians. They are in rads. And this theta is the angle in rads of the dark fringes with single slit diffraction. P equals 0 is the brightest fringe. I know this is weird because we're saying that P is the dark fringes. This is the exception to that. P equals 0 is the brightest fringe. It's at the center of the central maxima. All of the other p-values are dark fringes. This one is the exception. In finding, we can also find the distance to the dark fringes from the central maxima. That's what we did before, except with the bright ones. So we have so from this setup, we get yp is equal to L tan theta. Tan theta is approximately theta from the small angle approximation. We got this from the last page. So we can say that the distance from the central maxima to the first minima, or the distance between the minimas, is yp is equal to P lambda L over A. So that's lambda L. All those should be the same size, they're just not. Those are the positions of dark fringes in single slit diffraction. To find the width of the central maxima, the central maxima again is odd with the central maxima is different than it is with double slit diffraction. In this case, you'll see that it's actually twice as large as the other bright spots. Technically, dead center should be a minima, but it's not because there are other waves that are interfering. Center should be a minima, but it's not. So the central maxima is actually twice as large as the other. It's twice as large as the distance between the other ones. It's twice as large as the other constructive interference spots. So it's 2 times yp, where p equals 1. So the width is twice this. The width is twice this distance. So that's between 1 and 2. The width is twice that distance. We got that value from above. And we can say that W equals 2 lambda L over A. As the length increases, so as the distance between the slit and the screen increases, the width of the central maxima increases. As A increases, so as this slit gets bigger, the width of the central maxima decreases. So if this slit here is very large, then the central maxima will be very small. If this is very small, the central maxima will be very large. That is going to end Chapter 17 notes. Hope that was as much fun for you guys as it was for me. And this is going to end our first installment of Not the Ideal Medium for Teaching Physics. Hope to see you soon.